Hi there. How y'all doing? We're looking at section 1.3 today, which is on systems of linear equations. Let's go ahead and get started. All right. We have a shorthand notation for linear combinations. It's called the matrix vector notation. In this notation, we group all of the vectors together to form a matrix. Then we group all of the coefficients together to form a vector. We write the matrix and the vector side by side, with the matrix always on the left side of the problem. So let me show you an example. We have this linear combination right here. So the weights are 3, -2, and 1, and the vectors are 4, -1, 6, 3, 7, 8, and 2, 2, 3. We're going to rewrite this linear combination using the matrix vector notation. The vectors group together in the same order, but they group together into a single matrix. So 4, -1, 6, 3, 7, 8, 2, 2, 3. And then the weights are listed separately in a vector 3, -2, and 1. These two notations, this here and this one up here, mean the same thing. Whichever notation you use is a matter of preference, but you'll see both of them in use from time to time. So they mean the same thing. We're going to get a little practice with this notation, though. So let's try another example. In this one, we want to write this linear combination in matrix vector notation and then compute its value. So the first thing we'll do is we'll group the 1, 3, the 2, 2, and the 5, -1 together. And those form a single matrix. And then we group the weights together, 4, -1, and 2, and they form the column of weights. And so that's the matrix vector notation right here. And then to compute its value, the first weight goes with the first column. So 4 times 1, 3 is 412. The -1 multiplies by the next column, so that makes the next column -2 and -2. And then 2 multiplies by the last column. And so when we multiply the last column by 2, we get 10, -2. So in the top row, we get 4 minus 2 plus 10, that's 12. In the bottom row, we get 12 minus 2 minus 2, and that's 8. And so that's the value. All right. Okay, let's move on. So there's a definition here. A system of linear equations is, go ahead and turn this off so you can see the whole definition. Wrong one. Try it again. There we go. A system of linear equations is a set of one or more equations that have on the left side of the equation a sum of variables that are multiplied by constants, and on the right side just a single constant on the right side of the equation. And a solution to a system of equations is just a set of values that if we plug in a1 where x1 goes, and then we plug in a2 where x2 goes, and then we plug in a3 where x3 goes, and so on and so forth, then the equation is correct, that both sides are equal. All right? So let's see an example of a problem that we can solve using a system of equations. All right. We want to determine whether this vector b is a linear combination of the vectors 1, 3, 0 and 2, 5, 1. All right. So let's give this a try. What we want to know then is there a weight that if I multiply 130 by the first weight, and then a second weight, 251, and I multiply that vector by the second weight, and then combine them together, does that combination add up to 1, negative 1, 3? Is this possible? That's where the question mark comes in. If I can figure out an x and a y that make this work, then we have a linear combination. Well, I can rewrite this linear combination by just writing out the each row. The top row says x times 1 plus y times 2 equals 1. That's this equation here. The second equation says 3x plus 5y equals negative 1. That's that equation there. And then the bottom equation just says that y is equal to negative 3. So we already know what y is. Y is negative 3. And so now we can solve for x. So if we look at the first equation, we get x plus 2 times y would be negative 6 is equal to 1. And if x plus negative 6 is equal to 1, that means that x is 7. And now we know what x is. But we have a problem, because if I look at the second equation, 3 times 7 plus 5 times negative 3, that's 21 minus 15, and that doesn't equal negative 1. That equation does not work. These are not equal. And therefore, B is not a linear combination of V1 and V2. So the answer is it is not a linear combination. We looked at the equations, we figured out what y was, we figured out what x was, but then there's a third equation and the x and the y values don't check in that third equation, and therefore this is not a linear combination. So we have an answer. Let's try another problem. This time, we're going to show that B is a linear combination of V1 and V2. All right. So let's give this a try. This time we want, my weights are going to be x and y. We want negative 2x and positive 2y to be 4. And in the bottom equation, we want 5x and negative y to be 6. So this is what we want. Now, there are a bunch of ways of trying to solve this system of equations. My favorite is to cancel one of the variables. So what I'm going to do is I'm going to multiply equation 2 by 2. That is, I'm going to rewrite this as negative 2x plus 2y is equal to 4, and 10x minus 2y is equal to 12. Because now if I add these equations together, the 2y's cancel. So we get 8x, the 2y's cancel, is equal to 16. And therefore, x is equal to 2. All right. So we now know that x is equal to 2. So let's figure out what y is. So I'm going to look at this equation here. I'm going to change colors a second. 5 times 2 is 10 minus y is equal to 6. And therefore, y has to equal 4. So now we know what y is. But we want to make sure that these values check in the other equation. So does negative 2 times 2 plus 2 times 4, does that equal 4? And that answer is yes. Negative 2 times 2 is negative 4. Negative 4 plus 8 does equal 4. And so these values check in both equations. And so yes, 4, 6 is a linear combination when we multiply the first vector by 2 and the second vector by 4. And we have an answer. All right, let's move on. So let's show by graphing that 4, 7 is a linear combination of these two vectors, v1 and v2. All right. So let's make this happen. So we saw this before where we extend some dotted blue lines to meet out at v. So the first part of the linear combination is going to be v1. And so I'm going to take this line v1, the line that goes through v1, and I'm going to go ahead and extend it. And somewhere on that blue line is going to be the first part of the trip that will end at B. So we're starting out here, we're traveling in the V1 direction. Now the second part of the trip ends at B, but the second part of the trip goes in the direction of V2. So what I'm going to do is I'm going to draw a parallel line to V2 that goes through B. So we extend V1, and then we draw a line parallel to V2 through the head of vector B. And they cross right here. And now we have to figure out how many V1s and how many V2s are needed. So if this is V1, then this is negative V1. So we know how many V1s we need. We need negative V1. And now we have to figure out how many V2s we need. So 1 V2 gets me here. A second V2 gets me here. 3 V2 gets me here. 4 V2 gets me here. Did I do this right? I should probably draw these lines a little bit more carefully. Yeah, this is going to meet a little further over. It's going to be 5 V2. It's going to take a fifth V2 to get up to here. Draw this a little more carefully than I can do this on the tablet here. And so what we have discovered is that 4, 7 is negative V1 plus 5 times V2. So that's 2, 1. Does that check? The top row is negative 6 plus 10. That equals 4. And the bottom row is positive 2 plus 5. Positive 2 plus 5 does add up to 7. So that checks. All right. When we write an equation that looks like this, the matrix is given, but the vector that's beside it is not given. This is our variable. That variable contains the weights in a linear combination. So we're trying to find those weights or those coefficients. So since we have three vectors, we need three weights. So in this problem, x is going to be a vector that has three coefficients in it. Let's try an example. Let's solve this equation here. So in this equation, we have two columns in our matrix, which means we need two weights. And so we need a weight for the first column, and we need a weight for the second column, and that gives us the equations 3x plus 2y equals 7, negative x minus 2y equals negative 1, and 4x plus y is equal to 11. All right. Bunch of ways of solving this, but again, my favorite is to eliminate a variable. And so I'm going to add these two equations together. So I'm going to add equation 1 and 2. So when I add those together, 3x and negative x is going to be 2x. 2y and negative y is going to be 0. 7 and negative 1 is going to be 6. And so x is equal to 3. So then let's look at equation 3. So now equation 3 says that 4x, so if x is 3, 4x is 12, plus y is equal to 11. And therefore y is equal to negative 1. Let's make sure that that answer works in all three equations. So in the top equation, we have 3 times 3 is 9, plus negative 2 is 7. So that equation checks. This is going to be negative 3 minus 2 times minus 1 is plus 2. Negative 3 plus 2 is negative 1. That equation checks. And 4 times 3 is 12. 12 plus negative 1 is 11. So that equation checks. And so our solution is that x here is the vector 3 and negative 1. All right. Let's try another one. As we start covering matrix-based techniques for solving these systems like this, we're going to want a notation to talk about specific elements in the matrix. This is called index notation. We'll write a variable with two subscripts to it, and that will always reference the row first and the column second. So in this example, if I want the value of A21, this notation here means row 2 and column 1. So that's going to be this entry right here. A21 is equal to 5. All right. So we're just seeing some notation to talk about the method that we're going to be building up towards. We have a system here that has 4 variables, 4 weights in the system, and 2 equations. If I put all of the information in the system on the left side into a matrix, we call that the coefficient matrix. The coefficients are 1 and 5, then negative 3 and 1, and then 2 and then 8, and then 11 and then negative 6. When we describe the size of this matrix, again, the number of rows go first. And so we say this is a 2 by 4 matrix and not a 4 by 2 matrix. We could also keep not just the coefficients, but the constants in the system as well. And we call this an augmented matrix. The coefficients are 1, 5, and that's the first column. Then negative 3, 1, that's the second column. 2, 8, 11, negative 6. And then we're also recording the constants 2, negative 7. So we have both coefficient matrices and augmented matrices. The first non-zero value in any row of a matrix is called the leading entry, or the pivot entry of that row. You'll see both terms. I usually say leading entry. Our book usually says pivot entry. Just be familiar with both of them. Leading entries are simple. It's just the first number in every row that's not a 0. So in the top row, the leading entry is a 3. In the second row, it's a 4. In the third row, it's a 5. And in the fourth row, it's a negative 8. That's it. And finally, we say that a matrix is in echelon form if the leading entries are ordered in left to right order. So if I have a leading entry here, the next leading entry has to be somewhere to the right of it. Their next entry has to be somewhere to the right of that. We can skip over a column as long as we move to the right. It might be that we have a row that doesn't have a leading entry, but that would mean that the row has to be all zeros. If it doesn't have a leading entry, every entry in the row has to be 0. We put that entry at the very bottom of the matrix. So these matrices are in echelon form. My leading entries move left to right. I do skip over column 2, and that's okay. I don't have to have a leading entry in every column, but the leading entries have to move left to right. This matrix is also in echelon form. The leading entries move left to right. We run out of entries, and we have a couple of rows of all zeros at the bottom, but that's okay. The leading entries still move left to right. These matrices are not in echelon form. My leading entries do not move to the right here. And this is not in echelon form because there's a row of all zeros that's not at the bottom. That's not at the bottom. All right. Every matrix, and I mean every matrix, can be converted into echelon form using a combination of just 3 steps. One of the steps is we're just allowed to swap the entries in 2 rows. If I have a row that's out of order, I can just move it around to a different row in the matrix. I can scale a row. I can multiply the entries in an entire row by a non-zero constant. And here's where we're going to use linear combinations. We can replace a row with a linear combination of that row in another row. Okay. So let's put these to use here. All right. These matrices are not in echelon form. What we're going to do is we're going to do one operation on each matrix that will put it into echelon form. So see how this works. The first matrix. Why is the first matrix not in echelon form? It's not in echelon form because the leading entries don't go left to right. They go right to left. And if the leading entries are going in the wrong order, then what step will let us put them in the correct order? We're allowed to switch the order of the rows. Well, that's one of the things we're allowed to do. And so we're going to move the second row up to the top and the first row down to the bottom. And so now my leading entries are in the correct order. So why is the second matrix not in echelon form? Well, the leading entries are not moving to the right. They're just both in the same column. And so what I need to do is move this leading entry over here, which means I have to change 3 to 0. The way I can do that is I can use a linear combination of the 3 and the 1 that will add up to 0. Let's see how that works. If I take the third row and subtract 3 times the first row, that's not the third row, that's the second row, sorry, minus 3 times the first row, then 3 minus 3 is 0, and 8 minus 6 is 2. So I've replaced the bottom row with a linear combination of 2 rows. And that's something that's allowed to do. That's the third step that we're allowed to do. And it changes this 3 into a 0. So in the third example, again, the leading entries are not in left to right order. I need to make this 2 into a 0 so that the 5 will be the leading entry or whatever is there. So I want to change 2 to 0. Which means I want to find a linear combination of 2 and 3 that add up to 0. So the easiest way to do this is to think about what their lowest common multiple is. And that lowest common multiple is 6. If I scale one of these to be 6 and one of these to be negative 6, then when I add them together, they cancel out. So let's see what happened. Lowest common multiple is 6. So if I do 3 times row 2, that will give me a positive 6. If I do negative 2 times row 1, that will give me a negative 6. And so 6 plus negative 6 gives me 0. And now I have to do the same thing over here. So 3 times 5 is 15. Negative 2 times negative 2 is positive 4. 15 and positive 4 gives me 19. So once I start doing a linear combination, I have to do it all the way across. I can't just stop once I get my 0. I have to commit to doing it to the whole row. All right. One of the properties of Railroad's operation is that every operation can be reversed. This is an entirely reversible process. And so you don't have to worry about getting stuck. If you get stuck, you can back out. 2 matrices are called row equivalent if we can transform one matrix to the other using row operations. If the augmented matrices of 2 systems are row equivalent, then the systems have the same solution set. And this is the thing that we're going to make use of, is we're going to use linear row operations to transform a hard system of equations into an easy system of equations. But they will have the same solutions. I'll show you how that works when we get to an example. All right, so let's give this a try. We want to solve this system of equations by writing an augmented matrix and then reducing it to echelon form. So on the next slide, I'm going to give myself some room. I'm going to delete everything except for the system of equations. So let's give this a try. Here's our system of equations. We're going to write an augmented matrix here. So the top row is going to be 1, 2, 1, and then 5 is the constant term. Then the next row is 2, 1, 3, and then -1 is a constant term. And then -1, 1, 4, and then -6 is the constant term. And our goal is to put this in echelon form. So is this in echelon form right now? And the answer is no. My leading entries do not move left to right. And the first entry that violates the rule is the 2. So this is not in echelon form. And the first violation is that the 2 needs to be a 0. Okay. I need to make this 2 into a 0 so the leading entry will be on the right-hand side of the previous leading entry. All right. So how do we change that 2 to a 0? I want a combination that will cancel out this 2. So I'm going to let this be a 2, and I'm going to turn this into a -2 by taking double this row, okay? So the step we're going to do is we're going to keep row 2, but we're going to minus 2 times row 1. And let's see how that works. So the top row is still 1, 2, 1, 5. 2 minus 2 is 0. 1 minus 4 is -3. 3 minus 2 is 1. And -1 minus 10 is -11. And that's a -6. All right. Are we in echelon form now? And the answer is no. We're still not in echelon form. Here are my leading entries. Our first violation is that this -1 needs to be a 0. The 1 is okay, the -3 is okay, it moved to the right, but the -1 is now back to the left. So the first violation now is that the -1 needs to be 0. And so we're going to have to do another row operation. I'm going to have to cancel this -1. And I can do that with a +1 just by adding the 2 rows together. So we're going to do row 1 plus row 3. The top row now is 1, 2, 1, 5. The middle row is 0, -3, 1, -11. And the bottom row, 1 and -1 is 0. 2 and 1 is 3. 1 and 4 is 5. 5 and -6 is -1. Are we in echelon form yet? Still no. Still not in echelon form. But we're very close now. The 1 is in the correct place. The -3 is in the correct place. But now I need to make this 3 into a 0 so that the leading entry will be over here in the third column. So I need to cancel out this +3. So the -3 right above it will cancel out that +3. And we can do row 2 plus row 3. So the first two rows stay the same. In the bottom row now, 0 plus 0 is 0. -3 and +3 is 0. 1 and 5 is 6. -11 and -1 is -12. And this matrix is in echelon form. Yay. All right. Once with the matrix in echelon form, we can solve this system by working from bottom to top. So start with the last equation. And work up. So the last equation says that 6x3 is equal to -12. And so x3 is -2. And we have an answer for x3. Then the second equation says that -3x2 plus 1 times x3, so 1 times x3 is -2, is equal to -11. So that says that -3x2 is equal to, add 2 to both sides, -9. And so x2 is equal to 3. And finally, the top equation says that x1 plus 2 times x2, but 2 times x2 is 6, plus 1 times x3, and 1 times x3 is -2, that equals to 5. That's saying that x1 plus 4 is equal to 5, and so x1 is equal to 1. And so we have an answer. Our answer is that x1, the weights x1, x2, x3, are equal to 1 and 3 and -2. All right. Now this takes a little while to get comfortable with. But the idea is we put this information in an augmented matrix. We check to see if it's in echelon form. If it's not in echelon form, we correct the violations in the order they occur. And then once the matrix is in echelon form, we start at the bottom and we solve our way up to the top equation. And that gives us a solution. Right? Let's try another example. This system, we're going to solve this system by writing an augmented matrix and reducing it to echelon form. And once again, I'm going to put just a system on a blank screen so I've got some room to write. Let's try this one. 2 plus y is equal to 1. 2x plus y is equal to 1. 3x plus 2y is equal to 2. X minus y is equal to 4. All right. So our augmented matrix looks like this. 2, 1, 1, 3, 2, 2, and 1, -1, -4. My leading entries are in this column, so this is not an echelon form. The first violator is the 3. The 3 needs to be a 0 so that the leading entry is going to be the entry to the right. So the first violation we have to change. Change 3 to 0. So there are a couple of ways that we can do this. I can either use my lowest common multiple trick and make this 3 into a 6 and this 2 into a -6 and make this cancel. Or I can use the one below it and change the 3 into a, leave the 3 alone, but change the 1 to a -3. So let's try that. We're going to take row 2 minus 3 times row 3. So the top row stays the same. 3 minus 3 is going to be 0. 2, -3 times -1 is +3. So 2 times 2 and +3 gives me 5. And then -3 times -4 is 12. And so 12 and 2 is 14. All right. So let's give that a try. Then a bottom row is still 1 and -1 and -4. All right, this is still not an echelon form. My leading entries move from left to right in the top row, but then they go back to the left in the bottom row. So this is my first violation. We need to change this 1 to a 0. So what I'm going to do here is I'm going to take this 1 and use the 2 to cancel the 1 by making this into a -2 or a +2 and a -2. So we're going to take row 3 times 2 and then negative of row 1. So the top row is still 2, 1, and 1. The next row is 0, 5 and 14. And the bottom row now, 2 minus 2 is going to be 0. -2 minus 2 is going to be -4. And then -8 minus 2. Is that right? -8 minus 1 is going to be 0. I did this wrong. That's what's going on. -2 minus 1 is -3. And -8 minus 1 is -9. All right. So let's give this a try. This is still not an echelon form. My leading entries are 2, 5, and -3. And I want to make the leading entry move to the right. So I need to change -3 to 0. There's not an easy way to do this. So let's talk about this step. If I were to use the 1 to change the -3 by making the 1 into a 3 and canceling it with a -3, that would make this a 0, but because I have to do the entire row, that would change this 0 back into a 6. And I don't want to do that. So I'm going to have to use the 5 to change the 3. And the way that's going to be a problem here, is that 5 and -3 don't have a lot in common, so we have to go up to their multiple. I'm going to make this into a 15 and this into a -15. So let's see how this works. We're going to take the second row and multiply it by 3, and the bottom row and multiply it by 5. And this is what we end up with. All right, 15 and -15 is 0. 3 times 14 is 42. 42 minus 45 is -3. All right. This is now in echelon form. My leading entries are indeed moving in the order we want them to, left to right. But let's start at the very bottom equation. The bottom equation says that 0x plus 0y is equal to -3. This is my shocked face. That can't happen. This is impossible. And because this is impossible, this system has no solutions. All right. All right. Well, thank you for sitting through this video. I will have another one we'll have another one tomorrow. Take care of yourself.